Hello, and welcome to the Kettering University Auto Drive Team's Mid-Michigan 2021 presentation. So, we're going to start off by talking about our agenda. We're going to go over the results of our 2020 competition, and then we're going to talk about our challenges and progress in the 2020 competition year, as well as our goals for 2021 for each of our sub-teams. So, first, we're going to talk about our competition results. So, for those who don't know, our competition this year was held virtually via Pathable. That meant there's no dynamic portion of our competition, and the competition points were judged solely on any papers, reports that we submitted, and any presentations that we gave. During this competition, we got a first place finish in our technical reports, and a second place finish in the MathWorks Simulation Challenge. In the combined years 1 through 3 competition, this gave us a 6th overall finish, and for the year 3 competition, we placed 5th overall. The first sub-team we'll talk about is my sub-team, and that's the controls and simulation team. So, to start out, the challenges we faced this year, well, the first very obvious one is we were unable to meet in person. This was a little bit counterproductive in terms of working cohesively, but our team was able to use Google Meet to effectively meet once a week and other virtual methods so that we can work together as well as we could given the situation. More importantly, testing availability was a lot reduced this year. For the first half of the year, we couldn't test pretty much at all for reasons of 1, weather, and 2, COVID-19. So for this sub-team in particular, being able to test in the vehicle is incredibly important. Being able to see that your controller works in the vehicle as you intend it to is very important to make sure that you're going to be successful at competition. And just because you have a really good simulation, there could be some idiosyncrasies or differences or problems with your models that you might not find until you get to test in the vehicle. So being able to have that time in the vehicle, the second half of the year meant that we really had to work overtime in the second half of the year with a limited crew available and lots of other little things like limiting people in the car for social distancing reasons. And that allowed us to be prepared for the competition, but it was definitely a little bit of a hindrance for us.
I'm the leader of the integration and decision-making team of AutoDrive. So some of our challenges were limited access to the vehicle, much like the other teams. So we had the vehicle only accessible in the latter part of the year, whereas we needed it to integrate some of the functionality and to collect data from the sensors aboard the vehicle. We also had the problem of some loss of expertise from the last year. Some previous people had graduated who were very important to the team, so it took some time to get ourselves together and evaluate the state of the code on the machine.
The hardware team's primary focus for this year's competition was to install a passenger-side touchscreen display that is responsible for interacting with the vehicle's main computer. This design was meant to give the vehicle a more user-friendly feel while testing control algorithms and various other software components. The hardware team also sought to document all of the car's subsystem requirements and functional features via a user manual. This manual is meant to assist with hardware debugging and servicing. Since this past year's competition was held virtually, no dynamic events were judged. This presented a unique challenge for this sub-team due to the college campus closures and social distancing restrictions.
Hello, I'm William Wakefield, the mapping lead for the Bulldog Bolt team on the SAE International Auto Drive Challenge. I'm proud to say that in our past season, the 2020 season, we've been able to accomplish something under the mapping team that has not been done in the first 2 years of the competition, and that is creating a routing engine. The routing engine creates a pre-planned route for the vehicle so that it can know from destination A to destination B. And if there are any obstacles or issues in between the original route, it can also dynamically change its route to go around said obstacle, or if the pedestrian or if the passenger needs to go to a new stop. Kind of like when we're using Google Maps and we add in new stops when we're traveling or we're traveling around the city. Sadly, due to COVID, we were not able to perform or show the robustness of the routing engine in a competitive real-world scenario.
Hello all, my name is Magesh. I'm the Perception Team Lead. In Perception, we have several subtasks. The challenges we have for 2021 competition is testing. Due to the lockdown and weather, we can't able to test our code on time, which leads to backlog for several subtasks.
Despite all these difficulties, in 2020 we made a lot of progress. We developed 3 new longitudinal controllers and 3 new lateral controllers, and we were able to integrate all of them so that they worked on the car fully functional in preparation for the 2020 competition, even though we never got to drive the vehicle at competition. Additionally, for the simulation portion of our team, we developed a simulation that used all of our controllers in a closed loop in Simulink while utilizing the Unreal Engine for visualization.
So our 2020 progress was still able to do things, though. We were able to integrate lane detection into the vehicle by detecting lanes. We can do important things like lane keep and such. That's important information. They have the GUI prototype, so that takes in information from a watchdog that monitors all the nodes of the system and outputs a warning if that system goes down, so we can use that to better test and to better check whether the systems are working. We also have basic localization. So we have the map that gives us a path that we need to then translate into coordinates that are usable by controls. We have created that functionality. We've also created functionality for collision detection. So that detects whether we're currently going to collide with an object if we continue as is, and it also determines, given a certain step we are going to take, if that will result in a collision with another object.
However, much work was done in order to best prepare for the relevant design concept report and social responsibility report. Both of these articles go into detail about the car's subsystems, and it was critical that the vehicle's hardware was operational for all testing.
We've been able to show in theory that it can work in our Mobility Research Center at Kettering University. With our thanks to having that track there, we can see that it follows routes correctly. But when it comes to real world scenarios, we're hoping to see that happen in the 2021 season. In terms of other progress that we have made, not only on the vehicle but as a team, for the 2020 season, we've been able to grow into 9 full members, which is a lot in the context of the size of the Bulldog Bolt team. And because of that, we've been able to basically train a whole new set of freshmen that could help us with our goals and are dedicated to our next new goal for the 2021 season for the SAE International Auto Drive Challenge.
In 2020 competition, we integrated lane detection, pedestrian detection, obstacle detection, traffic sign detection and radar to the vehicle. Though we implement the task, we can't able to achieve 100% in our task. For example, in lane detection, we get a delayed response from the vehicle on detecting the lane lines, and we can't able to detect the curved lane lines. In sign detection, we can able to recognize the traffic sign and stop sign, but we get a delayed response on recognizing the sign. From the feedback received from the last year student, we are planning to make some changes.
Next, talk about the plans and goals our sub-team has for the 2021 year. So for lateral control, we want to take those 3 controllers and come up with 1 lateral control method that works using path planning for all lateral motion of the vehicle. Part of this will be a comparison study to compare different control methods to see which is best for our vehicle. Additionally, we'll be looking into grade detection so that we can use it to improve our longitudinal controller that we currently have. That will give us better grade performance when driving the vehicle in any situation. Additionally, we want to look into different control methods for longitudinal control to see if maybe there's another method of control that might work better for our team and for our vehicle. And finally, for simulations, we plan to add path planning to our simulation in conjunction with our closed-loop control simulation so that we can enter locations in the simulation and our simulated vehicle will just be able to drive there on its own.
We've also, in the future, we have plans for other things that goes further beyond these previous activities. So we have position tracking without GPS, which needs to utilize state information such as velocity in order to track our position, but also other elements as well. We also have obstacle avoidance we need to work on, taking that collision detection information and determining based on those functions what is the best path to take, one that will not result in a collision and which will advance us towards our goal. We also have the interactive GUI that we're going to be working on. So that we'll need to take in touchscreen inputs and interface with the rest of the system to both trigger autonomous functionality as well as input GPS coordinates and stuff like that. We also have localization with mapping functionality integrated into it. So there are a number of different inputs from mapping that we can receive, such as sign information, lane information, and that information needs to be properly combined with the information from both perception and our vehicle state information to better utilize it.
For future designs, the team plans on changing the camera mounts for the 3 inner windshield cameras. The way the center camera is currently mounted, it takes away most of the rear view mirror's functionality and creates a large blind spot looking forwards.
Supporting perception and the integration team heavily with important data from the high definition maps provided by here. These high definition maps, or HD maps, basically are the new way of helping us create a SLAM, or simultaneous localization and modeling localization model. With SLAM, with the HD maps can basically help perception with their cameras when we're at a four-way intersection with a traffic light. It can help perception know where the latitude and longitude of this specific light is, so that it can focus on the lights instead of having to look and compute the entire field of vision at once. So that way we can decrease computing resources, increase the efficiency of the SLAM on the car, and also help the car localize in a much more efficient manner. And that will be our goal for the 2021 season, and I look forward to it.
Our goal for this year is to combine both obstacle detection and pedestrian detection into a single task, since the ultimate goal is to recognize the objects that are in the road or may be hindrance to the vehicle. We are planning to implement sensor fusion this year to combine finding of an all sensor into a single output for decision making team. And finally, we are going to use radar to detect obstacles near to the vehicle.
So on behalf of the team, I would like to thank you all for watching our presentation, and we hope you learned something in the process. Thank you.